In this video, I will talk about how to determine phase constant in a simple harmonic motion. So here is the displacement x as a function of time for a simple harmonic oscillation. And A here is the amplitude of the oscillation, and omega is the angular frequency. And phi naught is the quantity we want to discuss today, which is the phase constant. So how to determine this phase constant? So phase constant depends on initial conditions. So let's say we set up a spring plus mass system, and the mass is pulled to a new position. When it is let go, it will start oscillating along this equilibrium position. So that's the equilibrium position. Doing oscillation along this equilibrium position. But let's have questions of when do we start timing this oscillation? When this object is released, you can start counting time right away. And that will give you a phi naught value. But now let's say we don't start timing this oscillation. We wait until the mass move to this equilibrium position, and then we start timing the oscillation. We say that's t equals 0. And then that will give you another phi naught. So again, it depends on initial condition. But in order to determine phi naught, we need actually two equations. So first one is the displacement. So suppose we start counting time when the object is at position x naught. That's the initial position of the object, of this object. And that will be a cosine. Because when we say initial condition, or when we say start timing the oscillation, it means that t equals 0 second. So we plug in t equals 0 second, get rid of this omega t. So we only have phi naught here. So that's one equation that we need to use to solve for phi naught. So we give you one equation. And usually this equation will give you two solutions. Phi naught, let's call it the phi naught 1 and phi naught 2. Okay, so suppose that you are not start timing, you do not start timing at the extreme position. Let's say this one is the positive A and that's the negative A. You're not start timing at least two positions, then you usually get two solutions. And those two solutions does not both fit the phase constant. We have to use the second condition here, which is about the velocity, initial velocity of the object. Okay, so velocity, as we know, is given by the derivative of position versus time. And if we have such a displacement equation, then the velocity is given by negative omega a sine omega t plus phi naught. So now if I plug in t equals 0 second, I get v naught equals negative omega a times sine phi naught. Okay, so we need a sine of v naught to determine or to differentiate these two solutions that we had previously. If the velocity, initial velocity v naught is positive, that means that sine phi naught should be negative. And one of the two solutions should satisfy that, and the other one will not satisfy. Okay, and that's the theory about how to determine phi naught. So now let's look at one concrete example. Okay, so let's look at this example here. Let's say I have an oscillation as a function of time, a displacement as a function of time, that is described by this picture. So now let's say at t equals 0, the object is here, it's at the maximum displacement, and its oscillation look like this. Okay. Now, when t equals 0, we know x equals positive a, so that equals a cosine phi naught. So cosine phi naught equals 1. And the solution here is unique between 0 and 2 pi in this range, which is 0, right? 0 degree or 0 radian. So that's the initial phase. So we already determined this example. Okay, so that's example number 1. Now example number 2. And also, by the way, in this case, you don't need the velocity information, right? Because the velocity is 0 at this point, so there's no positive or negative to talk about. Now, in the second example here, suppose the object has this oscillation diagram. Okay, that's a function of t, and the object start doing oscillation like that. Okay, so we have such a diagram, and at t equals 0, the displacement is also 0. Okay, so 0 equals a cosine phi naught. Okay, so now the solution here is given by plus or minus pi over 2. So we do have two solutions here for this setup, right, for this kind of setup. But how to determine whether it's positive pi over 2 or negative pi over 2, we have to look at the velocity. Okay, so initial velocity is negative omega a sine phi naught. Right, that's the initial velocity we just discussed. And if I look at the xt diagram, we know the slope of such a diagram is the velocity, right? Is the initial velocity. Slope at initial position, initial time is the initial velocity. And according to the diagram, such a slope is positive. Okay, so let's put a positive sign here. Now, in order for the whole product here to be positive, we need to have sine phi naught be negative. Okay, so we need to pick phi naught equals negative pi over 2. That is the only solution here. Okay, as a comparison, I would like to show you a third example. Now we have such a diagram. It's x. Oh, sorry, that's t. And that is x. Okay. Now the oscillation look like this. It going down and then up. That's the one period of the oscillation. Now if I do the same thing at t equals 0 second, the displacement equals 0, which is a cosine phi naught. So we still have the same solution as before. We have plus or minus pi over 2 as the solution to this equation. But now let's look at the velocity. Let's draw a slope at initial time. So this slope is the initial velocity, which is negative, right, since it's pointing to the left side. So initial velocity is negative omega a sine phi naught, and it need to be negative. So sine phi naught has to be positive. So we have to pick pi over 2, positive pi over 2, right, as the solution. So that's the initial phase. Okay, so I hope through these 3 examples, you know how to determine the phase constant in a simple harmonic motion, which is phi naught in this expression here.